And today, what I wanted to take a look at is, so first a quick introduction to this topic, right? To what I'm trying to do today. So I'm kind of like trying to go back a bit to the unsys GitHub. So I have this repo that I've been building that basically, so originally it was thought of as a simulator of sorts or a toolkit of sorts where I would basically take a state and evolve it, so represent the state of a system in a hypergraph fashion, and then evolve it, at the local level, just by keeping the correlations represented as hyper edges. And so by virtue of doing that, kind of obtaining a sort of a unique representation of the entanglement that is just not like at the state level, but at the qubit level. So for example, quirk, zo, quirk. So what you have in quirk here, right? If I do something like this, that's your typical Bell state where you kind of don't know what each qubit is at. It's just you can treat each qubit as a mixed state. We just know that at the system level, we're at the 0, 0 or 1, 1 level. And so the way that you would go and represent these, I think, JS Paint app. So the way that you would go and represent these by, and does this work or not? No, it doesn't seem to work. My pen's not working. Maybe I don't have it well plugged. Whatever. Maybe I don't have it well plugged. Anyway, I'll have to fix that. So, but what I wanted to do is itty thing. What's it called? Itty bitty, itsy bitsy or itty bitty, something like this. There was like a quick sort of thing to take notes. Just not to open the notepad, but I'll just open the notepad. Whatever. Who cares? So one way that you could do these, or the way that I envisioned that was, kind of say our system is in the, so if you have qubit 0 and qubit 1, so you would have qubit 0s in the 0 state and then qubit 1s in the 1 state. So each row would be a hyper edge, and each node is just, so this is a hypergraph with 4 nodes and 2 hyper edges, the hyper edge being each row, right? Of course, kind of each row would have like a weight associated to it, right? And so that would be, 1 over the square root of 2 kind of thing. God. So kind of, right? And so the way that you would get in the, in these states is by having something like, you would implement operations with rewrite rules. So you would say, we start off with just one hyper edge, right? That it looks like these because that's our initial state here. Then we apply a Hadamard. And so what the Hadamard rule would do is, so after the Hadamard, you would get that qubit into the 0 plus 1 state. And, of course, this is going to have weights inside here as well. And then what the next rule would do, and here's where things kind of evolved a lot in different ways in the past months, because I had different implementations of these. And at the end of the day, I kind of realized that everything can be done with rewrite rules. I had a sort of a low level implementation where kind of like was really doing matrix multiplication at the node or qubit level, but then I realized, well, a control node operation would take in 2 qubits as input, but because 1 qubit is not in the computational basis, the first thing that the rewrite system would do is actually split these into 2 edges, because essentially that's what you would kind of do if you think about like the linearity of these, right? So one edge would be like that, and of course then you get basically the coefficients in there, right? And So you would actually get something like that just as an in-between step, right? So this is an in-between step before applying the control X, just because it needs to apply the rules only work when the qubits are, say, in the computational basis. And now you can apply the control X because we know that here nothing happens, and we know that that actually in the second hyperedge something really happens, and then so you kind of have these, right? So that's the state that we wanted to reach. So that's the Roth idea. Then I think that I kind of deviated a bit because I started getting too much focused on how to map this to a wave function and how could I just get a wave function. I originally thought, look, each hyperedge actually corresponds to an element of the wave function. If your wave function reads something like like that, right? Then I would translate these to basically something like these, right? So that would be A, that would be B, and there you go. And then you can manipulate this stuff. But I think that kind of brought me down the wrong path, because then I just realized that it's kind of just starting building something that was just helping me um, manipulate wave functions in a way that it really didn't bring a unique representation of this entanglement. Like I wanted this to be a tool where then you could kind of analyze complex systems and with multiple qubits, and then kind of try to understand how the entanglement is there. But then I just realized that if I allow these to be just to have this mapping one-to-one to the hypergraph, I'm just left with something which is really not different than by hand trying to factor things out. Because how do I know that this is entangled? I kind of have to have a bit of a, then the manipulation set up in here to kind of simplify these. And at the end of the day, if you take a look at the code base, that's really what it's doing. And this is, I think, pretty dumb from my perspective. So I've got like a bunch of functions in here that say, hey, merge hyperedges if they're the same, or simplify hyperedges, or decompose hyperedges. And I think in retrospect, that was the wrong way to go, because ideally, this breaks down when you have something like that. Let's say that now I have two more qubits in my system, and I do the same to them, right, independently. So now I have these, right? So I have two systems which, it's funny because each qubit is in a way mixed, right? But so the way you would go, or with the way you would go about this with my original idea was that you kind of have these wave functions, right? So the 4 zeros and these ABC are just the coefficients, right? So you have, what is that? That is the 0011, that is the 1100. Yeah, okay, cool. So you would just kind of have these, and then so you would take that, you would really just build a hyperedge from each of these, and then what? Like how do I get to the point where I know and I can tell that there's only entanglement between qubits 0 and 1 and 2 and 3, because that's what I wanted to do, right? I wanted to kind of find a way to represent these things, and it's just I kind of realized that solving the problem this way is just doesn't bring any value to existing tooling. That's just expression manipulation. This means you can just do just have regular whatever, SVD, like the matrix, whatever, decompositions or whatnot, like just have regular factoring manipulation ideas, and see if you can do that. And I just thought that just felt stupid. I kind of spent a lot of time or wasted a lot of time implementing things like these, where it's like, you can just, give the system 2 qubits and then it will just basically, kind of realize that there's a 0, 0 and a 0, 0 here. So you can turn that into 2 hyper edges, kind of extract that portion out. So the way you would kind of do this, right, and say, from so you could actually do something like this, right, and say, hey, factor these out, right? That's maybe not really accurate the way that I'm representing it here, but that would be because this is not, these are kets that make reference to different qubits, but like that would be the idea, right? Because at the end, yeah, that's kind of, that's kind of what you're doing. And then you kind of would say, you would do the same here, and because these actually refer to the same qubits, then you could actually abstract that and say, look, actually, this is nothing else than these, right? And so there you go. So that's not what I wanted to do. Like that's not the tool that I wanted to build. I didn't want to build something like these. And I think one of the things that I realize now is that coming back to my original idea of letting the circuit evolve instead of just, because that is something that it's just known to be, it's complicated. I don't know what's the complexity of the problem, right? But it's not just like you gotta just try. It's like solving for expressions, and you won't always get. It's not trivial to get to these for any given for any given wave function. And actually, I think the SVD method is the best way to go about it, which is basically you turn these things into, so you turn your wave function into the density matrix representation, and then try to decompose how's this called? SVD. What's the name of this? It's the decomposition, singular value decomposition, and you do these, and then that kind of leaves you with 2 matrices, say A, I think it's A times B or something, but then there's sort of another small matrix in between, if I recall well, which is basically what sort of represents the entanglement, right? But that's also not optimal, because that tells you just kind of, I think, this just kind of tells you the type of entanglement in general across the system. And I'm interested into having a more visual representation of how do the different qubits are correlated. And so I kind of then realized, after going through a lot of the physics stuff here as well, that that might as well be a way to go, in terms of taking a look at their rewriting system and seeing if I can implement something that is just really, a kind of an evolution-based system where, but I really don't have it clear myself. So maybe I was thinking I could use the stream to kind of just think through these a little bit, and at the same time take a look at what's the tooling available for from the Wolfram physics stuff. I think it brings a useful perspective to a systems description. I think even what is done in the Wolfram physics project so far is really just at the system state level, but not the subsystem correlations, so to say. Maybe that's useless, I don't know. But I was thinking along the lines of, implementing something like what I've just kind of worked through here, right? Because let's say that, let's maybe, if I fast forward and just take a look at this example here, at this moment in time, we kind of have, I'll just leave the weights aside for now, but you have Q0, Q1, Q2, blah. Q2, can I just Q2, Q3, right? And here's like a 0 and a 0. Here's a 1 and a 1. Here's a 0 and a 0. Here's a 1 and a 1. So I think that's, if you think about it, sort of a table way to represent that system, that would be it, right? So you have 2 hyper edges that only contain nodes of Q0 and Q1. and two hyper edges that contain nodes of Q2 and Q3. Now, I think the hardest part of all these is how do we evolve the system? Like, how do we evolve the system? If I now go and say, boom, I'm going to add a control NOT gate here. So sort of kind of bridging both things, right? Because now we have a bit of a different correlation here. We have the 0, 0, 0, 0, we have the 0, yeah, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0. Like they all still, from a qubit perspective, behave the same. But basically, I've got these kind of four possibilities. So, but how do I implement this here? Like, what would the rewrite rule system need to do? So the rewrite rule system, it's got some simple rules, right? So basically, I think rule number one, or sort of behavior, like the requirement, I would say, a requirement. So the requirement number one would be that a rule, so a rule takes a qubit map as input, and then what? And then what does it do? Does it match? A rule takes a matching statement or expression. A rule takes a replacement expression, right? So that's the idea. I think that's just the ideal signature of how the rule would look like. So you kind of have match these, replace for that, right? But you would do these in a way that then you kind of map that replacement to specific qubits, right? So if I would say, I don't know, for example, that will be all that it needs. So the rules that you would need for the CNOT would just simply be kind of these ones, right? So basically two rules, which is find, and the map would be Q0, Q1, right? So that would be the map. So you would say find these kind of things in the hypergraph and replace them by these things in the hypergraph. Now the complexity comes in when we've got things, because if we've got these pairs within existing hyper edges, that is then trivial. You just replace that. If that would be these, right? The execution of these rules would just turn these into that. Which would then in turn result in the merging of these two. So you're destroying the entanglement here, right? That's really another thing. So that would be kind of number two, non-computational basis nodes, right? That's kind of what I said. I think, that like if we would have a node in this state, the first there should be a pre-processing step where this is then split into two different hyper edges. And number three would be hyper edge merging or post rule. So after the match, you need to check whether hyper edges don't need to be merged, whatever that means. Like, I think, let me just do that. So unsys v1 will be let me check quickly the timing, and what do we have here? So That is what I think that is what I have in mind, right? But I need to understand. Okay, so the thing is, how does this matching happen really? So that would be 2, that would be 3, that would be 4. How does this matching? Because I think the mistake that I made last time was to kind of assume that the matching will happen at the hyperedge level. But what happens here? How can I consolidate that? Like, how can I evolve this system in a way that is meaningful, right? So I know I know my mapping. So I know my rule in this case will just have this mapping. So that's the CX, that's a control X, control to not operation rule. Yeah, okay, so give me a second. So that is actually, I can, basically interference, right? I mean, that is interference. Like if I have a something in the 0 state and then just a node, just one hyperedge in the node in the 0 state, then it turns into the +1 state. That will be the Hadamard rule, right? Then I apply another Hadamard rule, so that would actually split the whole thing into 2 edges first, and then apply 0 + 1 in that edge and 0 - 1 in that other edge, and then this and then I mean here there's kind of where interference is happening. And that's also an advantage of this simulation or this system, is that you kind of get to see the interference patterns. That's the idea, right? But basically, I'll just kind of trash the whole code and write back from scratch, I think. Maybe not completely from scratch, I think there's a good basis, but I'm also considering whether I just would not use whatever tools are already available in the Wolfram physics project, because I think there's quite some powerful rewriting engine here for hypergraphs. Why not use that, right? Software tools. That's what I. Look at these. I think I saw these. So this is the set replace. Okay, so that's actual Wolfram models is set substitution systems. Okay, that's something that I will take a look at probably. Where there's some. Oh, look at these. Okay, cool. Wolfram models. Yeah, I think that's probably worth taking a look at, because I probably can use that to exploit set and hypergraph substitution systems. Yeah, that is definitely probably a better place to get started, rather than just doing it from scratch. But maybe I could just use it. I could just build something by from scratch, because I think that is cool, because it probably, yeah, it actually has some cool visualizations in it, which is what I'm currently missing in my system. Yeah, but still, it would be nice to. It will probably be nice to actually try to do a bit of a from scratch kind of implementation of these first, and then take a look at using these tooling. And maybe that is something that I'll kind of, as part of learning the quantum mechanics stuff. Yeah, I don't know. I think I should probably keep both streams open, but I might do a little bit of an off-stream kind of work on these, and then or kind of just record videos. I don't know, and then at the same time go through quantum mechanics stuff. I think I should be able to keep both ends open, and hopefully stream more often. Although I've been saying that since like ever. Anyway, I'm trying to. I'm naturally just trying to avoid the hard part of these, which is how do we evolve these, right? So we have this system in here, and sorry. So we have this system here. That system here. Let me just. How do we evolve that? So now a control node comes in with a map to these 2 qubits, and what do we do? Like, is there any pre-processing that needs to be done? Because essentially, this is the whole system. What a control X is telling you is, essentially, let's try to stick to the rules, right? The rules tell me, find this pattern, replace it by this pattern. Find this pattern, replace it by this pattern. but I can't, like, so I have 4 nodes, 2 with Q1 and 2 for Q2, right? So I guess out of these, right, you can have 4 combinations. So you can have the 0, 0 or 0, 1 combination and the 1, 0 or 1, 1 combination. Um, which essentially I think there are 2 ways that one could go about it, right? So one could just say we're going to create 2 more 2 new hyper edges. No, why? No, that's not what happens, right? Um, although, because essentially, so these represent, a correlation between Q0 and Q1, a correlation between Q2 and Q3. Like if I didn't have any of these correlations, the way I go about it is just check. I think I have to check all possible combinations, right? Because essentially what this system is telling me here is Q1 could take value 0, could take value 1, Q2 could take value 0, could take value 1. What we know is that these things are correlated. So this means that, if it would take value 0, we know that for that specific thing, like you would also have a 0 in Q3, but that's all, and kind of we need to carry that with us. Um, but I'm not sure how should we model these. Like, does this mean that now, basically, because these 2 things are gonna be in a way entangled, that essentially what happens is you kind of have a sort of a step 2. You kind of have a 0 here and a 0 here, a 1 here and a 1 here. So basically, oh god, no, that's wrong. So you kind of would have to have both, right? So you'd have to have these. So what I've done is I've just kind of I've just distributed these, right? So obviously you can do these in different ways. You can also just distribute it there, but like the result should be equivalent. And now kind of I have all the possible combinations of Q1 and Q2 in here. And now the rule tells me that I got to catch this pattern 1, 0, which is there, and turn it into 1, 1. And then I catch this pattern, which is there, and turn it into 1, 0. Right? Which essentially leaves me with this system, where now what we have here is that we have a correlation across the 4 elements, the 4 nodes. And still the question, the thing is, still the question remains here whether there's anything that we can do to simplify this. But does this match what I saw in Quirk? That's question. So So we've got the all zeros. We've got the 0, 3 ones. Okay, I guess that's because it reads this way. Then we've got the 1, 0, 1, 1, which is this one. Yeah, so that matches the 1, 1, 0, 0. Okay, so it just kind of like, because I think that's basically Q3 to Q0 to Q3 or something like this, whatever. Um, okay, but still, like, I think still that leaves me with the uncomfortable position that I really don't have a solution to kind of determine, like, cool. So what if I now do another control X and basically undo what I've just done, right? I kind of want to be able to go back to my previous system. So that would be an essential step, right? So an essential feature of this whole thing. Because what I want to avoid is that, like, now I have this really neat representation that tells me what are all the different correlations between different qubits. There are 4 possible different correlations, but I don't know if that's entangled. Like, in theory, if I take a look at these, I would have to do some sort of factorization algorithm on these to make sure that things don't interfere, merge, or whatnot, right? Um, so I know that it's not because I know that, right? But what if I now evolve with another CX? So I apply another CX, and then I see here that the both qubits share edges, share hyper edges. I think that would be probably a case one, all hyper edges are shared. That's kind of the easy case. Case two, some hyper edges not shared, and that's kind of where, or that's rather case one, and that's rather case two, right? In the sense that that's the first case, and when I apply the second Hadamard, that's the case, because all the hyper edges are shared between these two qubits. So now I apply the rule, and it tells me that 1, 0 should be mapped to 1, 1. So I go here. Let me just copy that. And I'm matching 1, 0 to 1, 1. So that goes back to 1, 1. And I'm matching 1, 1 to 1, 0. So that goes back here. And now, but okay. One thing that makes these probably easier is that I know that I've only changed these 2 qubits. So I don't really need to check across. So I just need to, I need to, the advantage here is that I'm not starting from a zero knowledge, like, hey, that's my wave function, that tell me what it's entangled. I know that I've just hatched. So if I assume that after each rewrite step, I have sort of the already factorized version of it, like, if that's my state. That's the only way I can factor things. And then I go here and I say, okay, I apply this rule, right? And I think this post processing for the factoring stuff, or for the I guess after the matching, would be, okay, I've touched these 2 qubits. Can I separate them? The only way that I could separate these 2 qubits, right, is if I have something like this. This means that I just have a well, I just have a sort of an all combination of those. So so I can basically, because they repeat. Okay, so there. But taking a look at Q1 and Q2, I know that I have sort of, from a combinatorial perspective, I have all the combinations. So I know that I should be able to just cat through, right? And kind of go back to these. That's the idea, probably. So what if I would do another operation that would disentangle that as well? For example, if I would, so here I have 0, 0, I have 1, 1, 0, 1, 1, 0. Okay. But yeah, essentially I have here that as well. I have all the different combinations. So why can't I split that? That's the complicated part. Mm, 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 mm. Because I've come from here and I've just touched, I've essentially messed with these, but essentially I still have uh, all the combinations 0, 0, 0, 1, 1, 0, and 1, 1, right? It's just that um, if I take, for example, the 0, 0, I've got a 0, 1, 0, 1, and the 1, 1, I've got a 1, 0, and 0, 1. So this is then everything really entangled, right? Um, but I don't know how I would detect that. That's the issue. Without having to do any like factorization algorithm, right? That's the point. I'm trying to see if I can evolve this in a way that on a step by step I can kind of keep the factorized correlation set, so that I know at all times if there's a entanglement and how the entanglement looks like, right? But as you can see, if I come from step one like this, and all I've done is change these two by these two, like I don't really know how I would simplify these. Like I guess what I'm trying to say is the execution of one single operation. I find it awful, like that. Just the execution of one single operation just makes that problem right away just complicated, instead of just making maybe a version of a simpler thing. Like maybe I should keep track of these things in a separate way so that it's easy to do that. So if I, because there's no difference, as I said, like between these, like I just have to analyze the whole thing to know that, and I don't want to do these. Now, what if instead of saying, okay, now I have a C node between Q1 and Q2, and what I will just do is I will create new edges that reflect that, right? So I will say, look, there is, so for the combinations, I know because there are multiple combinations, but I'll say for the combinations 1, 0, and 1, 1, right? So I'll say, so I will not touch these correlations, and I will just add more information to these and say, basically, kind of add both, right? Because they don't share edges. So now I'm just going to create these edges and say 1, 1 and 1, 0, right? Because I just, yeah, but still, that is just doesn't feel the right way to do things. And 1, 1, 1, 0. That's also not true. That's also not true. Okay, let's do it this way. Actually, no. So look at this. So I think maybe I can just keep track on one end. I have these here, right? So I know the only correlations that matter are when that's damn hard. That's damn hard because I don't really know what's the best way to keep track of these. That feels the most natural thing to do, but then it just fucks it up. Like, because I don't know if I can split stuff unless I would just take a look at the other elements, right, and say that's still simpler, because if I have a more complicated system where I have other kind of subsets or other sets of entanglement pockets, so to say, I don't have to look at them. Like, if I would have like 4 more, then I would have like a huge wave function, and so this would still provide a benefit over that, because what I can definitely do is I can check here if I can factor this out. This means I just have a factoring problem that it's smaller. And the way that I will be able to factor this out is by just taking a look at if for this combination of 0, 0, I have a 0 and a 0 and a 1, 1. Oh God, but why? But then I also need to check between Q1 and Q3, don't I? Because there might be multiple ways to factor these. So I need to come up with maybe a sort of a local factorization step in here. Like, I'm not so sure if it would be naive or not to just say, I know, because I just run the rewrite rule, I know that I've just changed Q1 and Q2. So I know, so now I need to check if I can split between these two, right? Because that is sort of a local operation from a qubit level perspective, and I know that this couldn't have affected anything else in the system, just these two nodes. So I need to check, can I factor here? Can I split Q1 and Q2? So can I put Q1 and Q2 in different hyper edges? And therefore, yeah, okay, but then I need to check whether I can separate Q2 and Q0 together or Q1 and Q3 together. So that's also not trivial, right? Because at that point, I don't know. but I know where can I split, and so I would just need to check for that. So I need to think about an algorithm for these. And again, it all has to work symbolically speaking as well, right? Because the whole thing is that I also want to make sure that one can use symbols instead of these stuff, and then you have the weights involved in there as well. But it feels almost like there's no other way to work around this, because that is a faithful representation of the entanglement. That tells me, and that's something that's going to become expensive as the entanglement grows, because the more entangled things are, the more information you've got there to represent. But I don't know. I'm still open. Is there another way I can represent the rewrite? I can run the rewrite rule of a CX here, and if not, what's a way that to locally factorize something like these? That's probably what I should be focusing on. So yeah, I think I'll leave it here for today. It's been a bit of a recap for these as well, and definitely a challenge. And I will see if I can take a look at these and see if I could use some of this stuff in here, because that is actually pretty cool. Status edge indices, all edges throughout evolution, events, because there's a lot of things that you can do here that I can definitely benefit from later on. But again, still, my goal would be implement maybe first something that is just a local version of these, and then move it to the Wolfram stuff, to the set replace stuff, which is pretty cool that it's actually open source. So, oh god, I got a lucky in. Okay, I'll do this later. Anyway, awesome. Thanks for watching, and stay tuned for more soon. Bye bye.